You guys are the hardcore guys, right? 4:15 and still here. You guys had coffee? You're awake? Okay, we have 90 minutes, I think. It's only about 80 slides, so we should smoothly sail through this. We go a little bit into something called VXLAN EVPN. Hope you have heard of it a little bit. It's something kind of encapsulation and control plane. We talk about what these different things are. And I have a starting section and an end section, which is packet walks. You guys like that? I was forced to make this what is called the 2000 session, which is intermediate. So I tried to speak a little bit slower. Generally, we do this as a 3000 advanced session at a little bit faster pace. But given that Cisco Live doesn't happen here in Australia at 8 a.m. on a Friday morning after the party, doesn't happen. My name is Lucas. I'm doing this for now. How many years, Mike? Lots of years. It's like a Groundhog Day, but I enjoy it. I was actually hoping that the weather is a little bit better, so I came in a Hawaii shirt, but didn't work out. We'll see next year. WebEx app, hope you use it. There's some rooms in there where you can write and ask questions. I'll try to have it as interactive as possible in the room, but I have a time management I need to do as well. So if you have a question, just write it into the room. I'll normally answer them on the flight home. Hopefully Wi-Fi is down, so I don't have to. No, joke aside. If you have questions, if you have idea, it's not only to ask me questions, but the whole group in here is probably joining that room, so you have expert to expert to go there. So we're going to cover a couple of different packet walks in there. We do L2 and L3, the simple ones. Then we will talk about what is actually VXLAN EVPN, if you haven't heard of it. What I'm not doing is going from the very, very beginning to an intro session, what it really is on the packets, on the control plane, and so on and so forth. That would be a 1000 session. I think it happened on Monday or so. Hope you were there. We go a little bit faster over there. One of the main parts in this session, as I try to merge a couple of pieces together, is I will talk about what is called multi-site. Anyone has more than one data center? Okay, that's how you interconnect it. So what does it help if you have only one VXLAN network in one data center? You want to interconnect it somehow. I'll bring that up there. And given that I want to have all of you falling asleep, I will talk about IETF and RFCs. Does that work too? Okay. That's the best thing for insomnia. You feel and fall apart and sleep right away. And then if somebody can explain me the difference between must and may. What's the difference? I have no clue. But supposedly there is a difference in this. So this is our agenda. Short intro, really, really brief. Layer 3 packet walk. Why do I do layer 3 first is it's simple. It's just IP addresses, right? And what do we have in bridging? This very cryptic other address, which nobody really can remember, but somebody had the glorious idea to use that same concept for IPv6. That's why we're not using it today. But bear with me, all of this applies to v6 too. It just looks differently addressing-wise. What is multi-site? I go down to a couple of architecture things, functional things, design things, IETF things, use cases of where you can use VXLAN EVPN beyond just one of the obvious thing, interconnecting data centers or so. And then last but not least, we go into a conclusion, which is literally one single slide. So don't run away when I show up that slide, okay? Please. That's normally what people do. They see conclusion, run for the door. He will never stop otherwise. So, introduction to VXLAN EVPN. It is very important that you understand what is happening on the wire, what we call the data plane, and what is happening in the protocols that drive the data plane, which is the control plane, right? Control, data plane, the two things in that world. So VXLAN is a data plane. It's an encapsulation. It's a take some kind of something and slap a header around it. In the specific case of VXLAN, it is always a MAC header-driven frame, and we're putting an IP header on top of it. It's literally what it is. So that means whenever I do something with VXLAN, I always have an inner MAC header because that's how the encapsulation is built. It's layer 2 encapsulation, and it's done in IP. So we have a MAC in IP encapsulation. Does it say it somewhere there? More or less it says it. The other piece is we're using UDP as the outer protocol headers. You all remember GRE, right? What was the outer header of GRE? Was it TCP or was it UDP? Neither. It was IP. What happens when I don't have protocols, I don't have source ports, and I don't have destination ports, so I don't have the option to create entropy, which means I'm pivoting only on one link and cannot do the variable of links. That's when NVGRE came in, which unfortunately failed, but VXLAN solved that by using UDP source port entropy. It's transport independent, meaning in a sense, the only thing it needs is IP connectivity between tunnel encapsulation points or VTEPs. That's all it needs. There's a little bit more. It needs about 50 bytes to accommodate that additional overhead VXLAN creates, meaning I have an Ethernet frame, I put an IP header and UDP header, protocol on top, plus the shim header we have there gives you about 50 bytes, 54 bytes in these cases. VXLAN as a data plane has a namespace. Same as Ethernet has a namespace. What's the Ethernet namespace? VLANs, right? Somebody had that idea, we put another header there, it's called a .1q header, we put VLANs in there. VXLAN has also a namespace that's stored in the VNI header, and it's a 24-bit field, gives me about 16 million identifier, which I can use. How many do we have in VLANs? About 4,000, right? And then I'll take a lot of them away from you because I have to have a reservation in some form or shape, and then suddenly we're at like 200 VLANs, right? You all run networks with 200 VLANs these days. Just kidding. 60 million identifiers. So with this, what I can do is I can create segmentation at a much more granular level. So I can do segmentation in two ways. When we go one level higher, I can do it as a layer 2 segmentation, layer 3 segmentation, which we normally refer to macro, or we can do something called GPO, group policy objects, which is more micro. So we're going beyond the part there. And VXLAN supports all of these different things in there. Okay, that's it. That's the intro to VXLAN. You guys are now the cracks. You guys are the guys, and this is EVPN. EVPN, the E stands for Ethernet, and VPN is Virtual Private Network. So guess what it is? It's a layer 2 tunneling control plane. So first time we have, not really the first time, but an early time where we put MAC addresses in BGP. Sounds like crazy, right? BGP is what? Border Gateway Protocol. It's a routing protocol. Now we create an extension where we can store what? MAC addresses in there, which is Ethernet VPN. So we created these routing templates if you want. So do a show IP route, you get an IP address back. You have something similar in EVPN, which gives you a MAC address back. If I would only do Ethernet, that would mean I only have bridging. That's quite a limited set of use cases. Why do I go even to overlay? I can use Ethernet right from the get-go. So what EVPN created as slight additions from the very beginning is additional use cases from a control plane perspective. So we added something which is called routing, magic. We added a default gateway, distributed anycast gateway, and that in combination is often referred to as IRB, integrated route and bridge. We allow mobility in the control plane. We do learning in the control plane. We have sequence numbers in there. We do multi-tenancy. So it just becomes a much more versatile thing. When you think of EVPN, it's MPLS layer 3 VPN on steroids because it does more than just layer 3. It does also layer 2. The reason why we invented EVPN back in the times is we had some kind of a deficient layer 2 VPN technology in MPLS called VPLS. It was flood and learn based. My endpoint discovery was kind of shady. My redundancy was kind of complicated. So EVPN covers all of these things. And that brings me to one of the bullet points which is up here. EVPN was not just built to make data center fabrics with VXLAN better. It was actually built to accommodate a whole bunch of other applications and encapsulation, which is one MPLS. So enhancing what we do with layer 3 VPN, also adding layer 2 VPNs to it. We have PBB, provider backbone, so we can do fully transparent tunnels in EVPN with control plane for discovery and extension of that whole story. Does that make sense? Obviously, no. I understand, but we'll get there. In order to bring you up to speed from an intro, what's the easiest thing to do? Let's look at network diagrams and put some things on it like name and numbers and a red dot somewhere. So this is a network device. Everyone agrees? If you don't know what to do, you do a circle. If you have no clue about anything else, you build a cloud. So this is a network device. Let's put that network device in the perspective of the rest of what happens in your data center itself. So we potentially have a server. That server is connected to the network device. So we have that host A over there. We will see that a couple of times. We have a host side, an access or a downlink to that network device. That network device, we don't yet know what it really is. It's a network device. And then similarly, we have that network device connected to the other side, our uplink or our fabric side, our core side, we connect it to a spine. I don't know why I can't see. Can you see that link in between? There should be a line in between these two things. Here I can't see it. I don't know if you guys see it up there. I need new glasses probably. So we make this network device and we put a topology around it, right? We have a network device, we have a spine, we have south of the network device something connected we call a host. And now I decide I put a function on top of the network device, which I call the VTAP, the VXLAN tunnel endpoint or the virtual tunnel endpoint. So the VTAP is a function on top of a network device. Very often we just say the VTAP is the network device. It's fine with me, but I want to be accurate and give you something that the network device and the VTAP are two different things. One is a function and application on top of it, the other one is the device itself. So when I add the VTAP on that network device, my network device becomes a network virtualization edge or an NVE. That is basically how we describe this in the formal language of what such a thing is with a tap on top of it. It's at the edge. But it's still a router, a switch, or a network device, or edge device, whatever you want to call it. It hasn't changed from a topology perspective where it sits. It sits between the host and the network, so it is the edge between the host networking part and the fabric networking part itself. Everyone good with this? Any questions to that? Damn, you guys are too good. So let's look at tables. This network device is a VTAP. We know that we have certain kind of tables in these devices. Some of the most obvious one is a MAC address table or a CAM table back in the times. Some other more obvious tables are IP routing tables. IP routing tables are often segmented with what? VRFs, virtual routing and forwarding. MAC addresses are segmented, or MAC tables are segmented with what? With VLANs. And then there is one thing. When you have a host and you are the default gateway for that host, there's one more thing you have to do. You have to map the MAC address table and the IP table together. What's the protocol for that? It's called ARP, so we have an ARP table, right? IPv6, it would be ND for neighbor discovery, so it would have an ND table. So as you see here, this NVE device will be my leaf in this very specific case. Remember we had the spine on one side, we had the host on the other side, so let's bring that back. Welcome host. Host is back. Host is attached to that NVE. Host is in a VLAN. Who decides that? The port configuration or the .1q header coming from the host. The host has a MAC address. Who decides that? The network card or the virtual network card. The host has an IP address. Who decides that? It's the IP stack you have configured on it. So this device here is, this host A device is what you did. Now, as that device shows up in the network, we learn a couple of things about this device. Traditional bridge-based learning, right? Flood and learn. Everyone heard of that? So we learn a MAC address on that Ethernet segment. We know it has an IP address configured. If there's an IP address configured and a default gateway on the host, In 99.99999 and so forth percent of the cases, hello, the host will ARP for the default gateway. If the host will ARP for the default gateway where its default route being set, I get the MAC IP binding information, the ARP table is filled. Then I have the ARP table filled, I know the IP address, I have the IP routing table filled. This is not even related to EVPN, this is just first hop routing kind of behavior. So let's add a little bit of EVPN into this conversation. In here, I have my spine is my route reflector, so there might be something more, right? Fabric side, there's a whole network there. And in that case, route reflector is a function of BGP. It's kind of helping to reflect information out. So we guess we have more NVs out in that network, a whole bunch of leafs. So I see there is an incoming update message from the spine, which is route reflector towards that NVE. This update message has a certain format, or NLRI, network layer reachability information, for EVPN. In this case, we are having, where is it? It's there. We are having an EVPN route type 5. EVPN route type 5 is an IP routing information. So there's no bridging info or anything in there. It's just for routing. It's for the layer 3 VPN use case if you want so. In the route type 5, we have a couple of fields. One of them is IP and length. Guess what? It doesn't have to be a /24. I can do literally any kind of mask I want to. I have a label. Guess what was the first encapsulation we did on EVPN? MPLS. Oh yeah, MPLS it was. So it's called a label, but in fact it would be the layer 3 VNI in the world of VXLAN. We have a route target, we have a next hop, and we have a router MAC. So let me go first to the route target. When you configure a VRF on a router on a switch, what defines that I have to import this route? It is not the name, and it's not the VNI or the label, it is the route target. So if a route object, like this route here, in BGP has a route target associated, and I say VRF, yada, 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 route target import based on this, that's when I will take this route and install it in my specific routing table. VRF name doesn't matter. VNI doesn't matter. The route target defines where it gets imported. When you do that import, which you see now here, I did import in VRFA, I decided that's my route target there. When I do that import, in VXLAN, I not only store the prefix, which is our network plus mask, we also have a next hop, and behind the next hop, we have the VNI. So we know if I want to send something towards that routing destination, with that next hop, in that VRF, I'll use this VNI to encapsulate it in VXLAN. You will see that in a second on the next slide when I show that up. But just very briefly, the route target is the relevant thing. Nothing else matters for VRFs. Anyone ever done route leaking between multiple VRFs? What are you doing there? Route target import, route target export. That's exactly what you do. You're leaking routes between VRFs. VRF is the local notation. If you extend it over a protocol, it's called a VPN. Here we go. That's why it's called Ethernet VPN. There are two more fields. I mentioned the next hop. Who is the next hop? The next hop is actually my remote VTAP who sent it to me, where I need to send stuff towards if I want to go there. And the last piece is what is called the router MAC. The router MAC is, how should I say, a little nasty little piece. Why do I need to know the router MAC for 1112, which is my next hop? Mentioned a little bit early, VXLAN is a layer 2 encapsulation. So the inner headers always must have a MAC header. This is my destination MAC header when I route to that remote station. So I cannot just leave it out. I need to keep it. I need to be complete from an encapsulation perspective. And I'm explaining you all of this because I will explain it now again with the VXLAN part added to this slide. So everything we just spoke about is control plane, yes. Local tables, we have not introduced any data plane specific piece yet. But when I want to send something from host A towards 10.10.10.77, up there at the very end, then my VTAP, my NVE device will start performing encapsulation or imposition if you talk MPLS. So in that process, I say I want to go from 192.168.1.11 to 10.10.10.77. Host A sends it to the first hop gateway, which sits on NVE. And then we're saying, OK, I'm not 10.10.10.0, but I know where 10.10.10.0 is. Where's 10.10.10.0? Somehow it's between 1112. 1112 has an encapsulation instruction because I received that over EVPN. So when I want to send something, I need to slap a header around. So I have to make a VXLAN imposition or encapsulation, which I'm going to do. You see there this inner IP part, 192.168.1.11, 10.10.10.77. You see A1, 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 A2, A2, A2. That's basically host A, source MAC and destination MAC of something which I actually don't really care. Yes? Is it the MAC address of host A? So what happens when I hit my first hop gateway and route further? A1 is the source MAC address of NVE. A2 is the remote MAC address of the router ID. So the two routers there route in between. I have a VNI of 50,000. Why do I do this? I got instruction in the route towards there. I want to do 50,000. And then I have the SIP and DIP, but this is the SIP and DIP in the outer space, meaning this is what we call underlay, how 1111 can reach 1112. How do we do this? Routed underlay network, that's a transport independence, which I mentioned before. Everyone able to follow? If not, it's not that hard, because I'll explain it again. As said, there is a sense to the madness in this whole thing. So now, we'll get a little bit more advanced. Now we want to do bridging. In bridging, host-to-host communication, in EVPN, we're using a route type 2. Route type 2 is a MAC IP route. MAC is mandatory, IP is optional. Why could IP be optional? It could be a non-IP host which wants to communicate. That is OK. MAC addresses in Ethernet are valid addressing. I don't need an IP. But if I want to do inter-subnet routing in some form or shape, I need to have an IP address in there. So the host route information are stored in a route type 2. You have their MAC and length. By the way, it will always be 48. You agree? MAC length is 48. Yes? Can we make it shorter? Probably not. We have an IP and a length, and the mask for that part can only be two different masks. One is 32, the other one is 128, V4 or V6. That's basically it. As we can do bridging and we can do host-based routing, we get two route targets. One is for my MAC VRF, for my bridging VRF, for my EVI. The other one is for my IP VRF, or the routing function. You remember we did IP just before, which was 65, what was it there? 65001 50,000. That was my route target for this one, label 50,000. And then I have another label there, which is 30,001 for bridging, which is 65001 30,001. So I have two VRFs now. I have a VRF for bridging, where I install MAC addresses, and a VRF for routing, where I install IP addresses. Who smoked that stuff? But If you want VPNs, you need build segmentation. And the segmentation has not only happened on the wire, it also has to happen in the box. I need to segment my tables, and you all did this. You did VLANs, and you did already IPVRFs for many, many years. The only thing what I add to it is I give you a label in a multiplexed form, and I give you the option to put both things on the same wire, but I want to separate it still when I install it in the box in a MAC VRF and into an IPVRF. Are you guys following? Okay, so we have this route over there. We have next hop, router MAC, still the same thing. We have two labels, and we're going and put these information into our local switch table. In the NV table, you see that the MAC address is being stored in there. And now suddenly, for the first time ever, a MAC address has a next hop IP address. Crazy shit we have here. It's absolutely unbelievable. But this is actually the VTEP address. So we're not egressing an interface anymore. We're going to a remote IP address, which is the tunnel encapsulation point, which we want to reach. So this is my direction to go. And yeah, not so magic, but we still have an IP address with a next hop there, which we saw before. The interesting thing is, I can store two different ways IP information, while I can only install one way MAC information. A MAC has a very distinct set mask length, 48. IP could have a variable length mask or a host mask. The host mask from route tab 2 or variable length from route tab 5. So I can see in this table here host routes or subnet routes. I don't know how much all of you look into switches. Mostly when we look at switches or routers, we say, yeah, it has 5 ports with 100 gig. That's all I need. I don't care. But what is a very interesting, essential thing over the last 10, 15 years, which happens, is how we built the ASICs and the respective TCAM tables or memory tables have become very, very different. In the past, MAC was everything, right? It was all about bridging. But these days, these routers and switches, which you're building, they have host route object storage of over 1 million. Can you imagine that? We're always scared about, oh, I can only store like 200 routes or something like that. It's not the case anymore. We are at a scale level in these modern switching infrastructure, the modern switching chips, which have a vast set of space to store routes. And not only to store host routes, but also to store variable prefix routes. So this box here, I'll show you a slide with the scale numbers somewhere, can pretty much store the internet routing table, which is somewhere in the, what is it, 750K? We're not in 1 million yet, are we? Anyone remembers? I don't. 1.1 million, I think, is this one. So let's look at the bridging operation. By the way, anyone can see that now my arrow is blue. The previous one was red for routing. This one is blue for. Here we go. You guys get it. So I want to do bridging from host A to whoever the other host is. And now you see that they're sitting in the same subnet, 192.168.111 and 112. Same subnet. Yes? So we don't do routing, we do bridging. So when we do bridging, we use the MAC information. The MAC information stay transparent. So you see 100A MAC address. Look at this. It's actually the MAC address of my host here, which is attached. And then I have 100B at the end, which shows me in the MAC address table here that it's behind 1112. So look at the outer DIP, outer destination IP address, the second piece in the blue frame there, 1112. That's where we send it, because what? The table told me before the control plane told me that this is where the stuff needs to go. You guys tracking? Was it too much? Because I have that again. No, I'm just kidding. Okay, so let's do a little jump. I need to get a piece in between, and then we're going back to the packet walks. You will see some of this stuff again, in blue and in red. I promise it. I promise it. In in the world of VXLAN and EVPN, everyone thought, hey, I solved my layer 2 over IP problem. Now I have tunnels everywhere. And that's one of the problems which showed up, which is tunnel proliferation. These tunnels are dynamically built, so it's an n squared minus 1 problem. Who is good at math? So we have about 60 people here in the room. If any to any needs to have a communication tunnel created, how many tunnels do we create? I don't know and I don't care, it's way too many. In order to make that a little bit more meaningful, I decide to separate my tunnel domains in my data center 1 and my data center 2. So I have 30 odd here, I have 30 odd here. So instead of letting all of you talk to each other, I'm putting a gateway in between and say, all of you talk to the gateway, all of you talk to the gateway, and the gateway talks to the gateway. Now when you do that so, I don't have anymore an n squared minus 1 problem because I have 30 in here who talk to each other and to the gateway, which is 1 tunnel from each of you, and I have the same thing over here. These guys over there and these guys over there never see each other, but I built transparent tunnels over the top. So the technology in order to achieve that is what we call multi-site. And it has nothing to do with data center interconnect. You can use it within a data center to build larger fabrics, multi-tier systems, and so on. When we started with all of this, there was an RFC which was called RFC 9014, which is the data center interconnect with EVPN, JBang kind of thing. You want me to read it? I'll do it for you. You will all run out. The RFC was defining how do I interconnect two VXLAN EVPN data center with a tunnel, or with EVPN itself. So DCI EVPN overlay was called, and this draft is actually phenomenal. There's a couple of little interesting things in there, so I'll show you one or two. Bear with me. There's a plan. You see here Fabric 1, Fabric 2, or DC1, DC2. We have two different ASs. We have these gateways there, and we stitch tunnels together. We have a tunnel domain left, tunnel domain right, and the gateways in the middle sit together. Now this great, fantastic RFC defines two different gateway modes. One is called decoupled, the other one is called integrated. This thing we do probably for 50 years now. What is the most common normalization layer in networking? An Ethernet .1Q trunk between two devices. So they basically defined, I have a VXLAN domain, I have an NVE, I take an Ethernet cable, I put it on a router, and I put some kind of layer 2 in between two data centers. Magic. Not really. The more interesting thing is the integrated gateway part, where we say we have tunnels inside. We terminate these tunnels, we create another tunnel over to the other side, and then build this thing, this fabric on the remote side on top of it. So integrated gateway, decoupled gateway. RFCs never tell you what you need to do with it. They give you options. The one option, I don't even have to do anything, because it's just a cable which I need to buy. The other option, I need to write code and define procedure. Now, I did this, we did all of this, but this little draft had a little problem, and I didn't tell you before, but what is with the routing part? The definition of the draft only addresses bridging use cases. Remember what we were talking before? EVPN route type 5, EVPN route type 2, bridging and routing. So you only have half of the story. And then where is multicast? Oops. Okay. So RFC 9014, great base document, but was incomplete. So we tried to bring a couple of things together, gave it a name, because somebody in marketing wants to have a name for everything. We called it multi-site. But what multi-site actually does is a draft definition, IETF draft definition, which gives you data center interconnect for bridging, routing, unicast, multicast. Do you think we reinvented the wheel and wrote something completely different? No, we did not. We just took RFC 9014 and say that's the reference for everything bridging. We took another RFC and this is the reference for all routing. And we put it together that it actually works together. And that's described in this multi-site document. So by the standards, on what we did is we created a use case draft. That's probably what it is. And we refer in this use case draft what we are doing. And we're doing stitching of tunnels, layer 2 and layer 3. And here, I'll give you a comparison as an eye chart between what RFC 9014 does and what the multi-site draft added to it. And there are two things which you will see. The route type 5 definition is not in 9014. It needs another draft to define that. We put that in the same in. And we created a couple of new kind of optimization for convergence and scale. Question. Who likes convergence in the seconds? So if you have a network outage, it takes seconds till the network converges. Who likes that? You like it, you don't care. You can wait. Milliseconds. How much milliseconds? As much so that the application doesn't figure it out, right? You want to have network convergence in the lower 2 digits to make sure that whatever happens, or even 3 digits for that matter, whatever happens, the network converges immediately before the application even will figure it out. And these are actually enhancements when you see up there, Anycast VIP. These are enhancements which we put in. The other thing is scalability. N squared minus 1 problem again. If each and every of us has an individual address, we need to talk to each and every one, right? But if I can hide multiple nodes behind one address and one disappears, will I even know that one disappeared? No. So my convergence is 0 at that point. Because multiple share the same personality in that case. So brief comparison, RFC on the left, layer 2. Multi-site on the right, uses 9014 and extends it with all the rest which we want and like, and no, we don't want to have convergence in seconds. It's a little side tour because we often talk only about intra-data center, which is great, but everyone has probably more than one data center, I guess. So these use cases which we thought about was to start with building smaller fabric in a single data center building. Why would we want to do that? Because less impact, less spread of potential failure or so. So in these cases, we want to make the point of we don't need a full mesh of communication in tunnels. We can slice it and dice it, build smaller, go fixed form factor switches instead of modular, and reducing the complexity of what you have to deal with. The other piece is scalability. It's a little bit old numbers, but we'll make it work for you. Who has single data center with more than 100 switches? How many? How many you got? 200? 500? Less than 200. Can you just say 500 or something like that? My buddy Mike in the back is writing down the opportunities for the refresh next year. Joke aside. As I reduce the amount of tunnels, which is actually what we call VTAP scalability or remote VTAP scalability, if I reduce that, I can scale my networks quite bigger. I did that before. I did it in BGP routing, and I did it in OSPF. In OSPF, we called it areas. We had area boundary routers, right? Same concept here. So we can build today 128 fabrics of 256 leaf switches. I'm not saying that you need this. Hopefully you do. But I can go beyond that magic number, which everyone came to me years ago and said, I need 1,000 VTAPs. Yes, did you build an Ethernet network with more than 32 switches? Probably not. So why do you need 1,000? VXLAN get that pretension, created that perception that you need 1,000. But now I cannot do 1,000, I can 32,000. I can extend layer 2, layer 3 across 32,000 VTAPs by doing hierarchical structuring of the network domain. That's all I'm doing. The same thing as what we did with routing protocol. Instead of building just flat everything area 0, I build area and OSPFs and I try to interconnect them. Do exactly the same thing here for the data plane and VXLAN in combination with EVPN. This is the example. The left side is tunnel proliferation. You see leaf needs to talk to every other leaf because that's the only way how it works. I can do a better way. I can say leaf talk to my local buddies, and then I let them interconnect so I can reduce the amount of tunnel neighborships and can scale out my VXLAN tunnel domain into the 32,000. Actually, the latest number is not 32,000. It is in the north of 65,000 taps or something like that. So in case you don't have enough, I'll have some in my back pocket to give away. Data center interconnect is another one. VXLAN needs two things, IP reachability and an additional 50 bytes of MTU. Whenever you can accommodate this, I can go and interconnect it around the world. Now, you probably have a question now and say, but what is with latency? UDP is the encapsulation we use, or the protocol for the encapsulation, which is VXLAN. We don't create a session. We're just sending it to the destination, right? So latency, I don't care. BGP runs on top of what protocol? TCP, reliable, doesn't care on latency. So I am not the problem on the latency side, but your application might have a problem because I cannot control what the round trip time is of where your application is falling apart. Technology-wise, I can build tunnels around the world. I probably should write a book about that. We can integration with legacy networks. So we call Ethernet legacy. Maybe you want to do a migration. Maybe you have a need for some other things. You have a small site. You have some catalysts or whatever else. You have some Ethernet network. And you want to build your new data center network with VXLAN EVPN. You want to interconnect it in a structured way. Put a border gateway on the right-hand side. Put a border gateway on the left-hand side. Interconnect it. Be done with it. You have layer 2 and layer 3 extension. You basically build MPLS L3 VPN without MPLS and L3 VPN. That was fast. It's VXLAN EVPN in that case. The other part, this one here, we did a couple of things with cloud service providers. These days, even in the public cloud, you have VXLAN EVPN connection points. Now there's one thing. The cloud doesn't do layer 2. So the only thing you extend here is layer 3. Just to be clear, this is only type 5 if I want to do my data center to cloud connectivity. So I was talking about this multi-site thing, and I remember I said border gateway, border gateway, border gateway, and I haven't defined it for you at all what it is. Border gateway is the function that makes the stitching of tunnels capable, and it's available on all of these switches. If I missed one, probably not. It's pretty much all of our Nexus switches we have today in the portfolio. The first release where we brought that in is somewhere in 2017. So we're not playing here with bleeding edge stuff, which just came yesterday into the code. We're having pretty much, I would say over 75% of VXLAN EVPN deployments with Cisco are running in some form or shape a multi-site architecture with border gateways, so pretty solid. These border gateways have a certain scalability number. One is the remote VTAP scale. You see there are a number of 256, that's the VTAP in the fabric, and I can do that 128 because every remote one is also a VTAP, so I can pretty much go into the 512. Latest number is probably more 1,000 and something, but you have a humongous amount of size of network you can build. And you remember when I was talking about the host routing tables? In the millions and not anymore in the 10Ks or in the 2Ks, so we can build rather big networks in that case. So I'll go back to this diagram which I used before for the RFC explanation, we're talking about border gateway. Border gateway are the integrated gateways from RFC 9014. It's the integrated gate from RFC 9014, which does not only layer 2 as defined in our RFC, it also does layer 3. So we do bridging and routing, subnet and host. It is the way how we stitch tunnels from an intra-data center fabric or tunneling system and in between. So if you want to go end to end from left to right, it's a tunnel from host to the gateway, from the gateway to the gateway, from the gateway to the host. So we slice that end-to-end tunnel in 3 pieces. Do we really care about this? No, because we do this at line rate. Our lookup pipeline for deciding if we need to stitch or not is done when that packet hits the gateway itself. And as we progress it through that pipeline in our chip, we already know where we need to send it, so we slap the header on and send it forward. You will not see a delay from a latency perspective on how the chip is performing this. When we want to look from an infrastructure perspective, how do we look at our TEP space or our next hop IP addresses? You see here the blue underlay, dark blue, some other blue or green, and we have the gray one. And you see that in blue and gray, the IP address space is completely separate. And they don't see each other because they will never build any direct tunnel from very left to very right. What they need to know is the exit point from blue whenever I don't know where to go, which gets me to the gateway, and similarly, when I'm over here, the only thing I need to know is the exit. And then between the gateways, what is the only addressing which needs to talk to each other? Gateway to gateway. So I split not only my overlay tunnels, but also my underlay networks apart, which gives me, from a troubleshooting perspective, another advantage, and also from a convergence perspective, because I only need to troubleshoot what? The inside of my data center, and can ignore what is happening in between. If you spread tunnels, you have to start at the remote side and roll slowly back. So this makes it simpler if you start going into that world. So these border gateways, we have 2 different types. One is called an Anycast border gateway, the other one is called a VPC border gateway. Why are we doing 2 things? Because you might have 2 different deployment modes you require. The Anycast border gateway is what we call a shared nothing. You can have up to 6 nodes in a cluster which are represented with the same IP address. So if 6 nodes have the same personality, all of them are called Lucas, like me. If one of the Lucases disappears, do you care? No, you just find another Lucas who gives you the answer, right? There is no other like me, just to be clear, very clear. So we can do up to 6, and we share nothing there. They're consistently configured. We have the first release in 703i7.1, which was Leaf, so we're very dedicated, and we added a spine function a little bit later because we wanted to make sure that we have proper testing and everything going. But in the meantime, we have customers doing it as separate nodes or collapsing with a spine. It's really your choice there. If I can say what my choice is, it's always separate functions because I want to sell more boxes. That drives the stock price up. But functionality-wise, we can do both. The other border gateway type is what we call VPC border gateway. Everyone heard of VPC? I would be scared if not. That's probably 20 years old now. VPC, virtual port channel, brings 2 devices together to form a single device. So we did this too. We used our VPC leaf and just added the border gateway function to the tunnel stitching function on top of it. This is kind of the case where you can attach hosts directly. So if you want to have a very little fabric somewhere remote at a co-location or something like that, you just need 2 switches, a couple of ports, boom, DAC, this is the one. Small data centers you want to connect your firewall to, done. Migration from Ethernet, done. We introduced that a little bit later. That came in 9.2.1. What does 9.2.1 mean? We are at 10.5 today. So again, this was not yesterday. This came a couple of years ago, 2019, I would say. So we have these two different border gateways. You see the Anycast shared nothing. You see the VPC border gateway, maximum of 2. And you see a little bit on what we think are good use cases for one and the other. The Anycast is fantastic for greenfield, stability, scale, very structured, leaf spine converged, or border gateway spine converged or separate, and then the leaves, versus the Anycast one, versus the VPC one, which is more like I have something small, I have to insert it in Ethernet network or connect something directly to it. From an addressing and personality perspective, I mentioned that Anycast has one personality, right? The Anycast IP address or virtual IP address, which you can see here on the left. So the Anycast border gateway, each of them has an individual personality for the routing peering relationship. I cannot do routing to multiple times the same person. I need to address them individually. From a data plane, they're all the same, meaning the next hop is always that VIP address, that virtual IP address, that Anycast address you see on the top there. So if one of the border gateways disappears, so what? There are 3 others or 5 others which do the job at that point, so configuration at a very low level. In the VPC border gateway, we first created the VPC leaf. You see the PIP address and the VIP, which is already there in VPC today. And then we say for the tunnel stitching, we add another address. So you can actually add and remove the functionality whenever you need, so you don't have to go and reconfigure everything and readdress everything. That's what you see up there with that multi-site VIP 10.0.2.1 on the right-hand side for whenever you need to do tunnel stitching with a VPC border gateway. It's not as dry in here yet like yesterday. 30 more minutes? You guys are falling asleep? Me too. So the control and data plane we discussed at the very beginning. You remember how EVPN looked like and how these type 2s and 5s and whatever existed. Then we have the VXLAN header, how the encapsulation gone. We're looking this again now with the multi-site spectrum. There are a couple of things we do with these border gateways, these gateway stitching, these integrated gateways, which helps us to make network environments more stable. There is, in BGP specifically, external BGP or eBGP, there is a function which is called the next hop treatment. So if I'm in AS1 and you're in AS2, you need to change the next hop when you send it further. It's a very traditional thing of what we do there. When we do this, we're not only changing the next hop, but we're also adding a list of transported ASs, autonomous system, in the route itself. So if I send a route to you, I'm AS1, you're AS2, you add it. As you send it forward, we know it came from AS2, 1, goes to 3, and when it comes back to me, what am I doing with it? I have a loop prevention in there. I know it's my own route, which I receive again, AS path attribute, so I don't really care about this. So when we built these 2 data centers, these 2 fabrics with 2 different autonomous systems, we get 2 magic things from BGP for free. The next hop treatment and the AS path attributes. Isn't that cool? I don't have to do anything else. It just happens magically. It's not as magically, it's actually exactly what the protocol was intended. So in the world of BGP, we have internal and external BGP, everyone aware of this? The internal one is actually not really a routing protocol. It's more of a reachability exchange, because you're not really changing the next hop, except you say, I want to change the next hop self. But there are a lot of things which are not present there, like the AS path attributes and the loop protection of it, which eBGP provides you. When we started with VPNs back in the times, sorry that I go with MPLS, but you all know MPLS layer 3 VPNs. I guess you have some references to this. It was always iBGP. VPN v4, VPN v6, always iBGP. Yes? And then somebody said, I need inter-AS options. That's what we asked for, right? And we created inter-AS option to introduce eBGP in the VPN world. Here, we didn't create a special option. We just used the next hop treatment. It's there. It just works. Now, there's a little caveat to this. You remember the router MAC, which I mentioned in that route update? When I change the next hop, do I also change an extended community at that point? And the answer is no. The router MAC is an extended community, so when you do a next hop propagation, you will not change the router MAC. So you need to have a function that actually understands if the next hop changes, the router MAC has to be the one from who the next hop is. You guys tracking? Yes? So that's when an inter-AS option for VXLAN EVPN or for EVPN specifically came in, which then became multi-site or that border gateway functionality. It works without that by 99% already, except that you have to go by hand and change the router MAC whenever you have a route re-advertisement you probably don't want to do, so we put that function in there. There's another piece I like to talk about, because I'm sure you all heard that every data center is using BGP as routing protocol, correct? It's the only routing protocol is BGP in the data center. We can argue about that. We already talked about the internal or iBGP and eBGP stuff. I'll give you a reason why in EVPN, our overlay control plane, the right way of doing it is iBGP within the data center and eBGP between the data centers. So I'll start the in-between. I just told you, right? Next hop, change, and AS path. That's why we want to have eBGP between the two data centers. It's an inter-domain routing case. That's where E comes in. Why do I want to have I within the data center? Because I don't want to deal with next hops. It's anyone to anyone within. The gateway treats the egress one. So iBGP, route reflector, single AS, super easy to do. You see this IEI on the top? Basically says iBGP within, eBGP in between. I heard that before. It was probably Internet Routing 101 50 years ago. I'm not that old, sorry, but that's how the intention was of these protocols, how to use. You remember when I spoke about the underlay part, where I said there are two completely separated underlay domains? When I use a different protocol for the underlay than for the overlay, they are completely separate. So I use an IGP within the data center. Makes it simple. eBGP between the data center makes it simple. Now, because you can and you want, I want to use eBGP everywhere. Be my guest. You can do it. Feel free. But you need to filter out all your underlay tabs. So from data center 1, they don't go to data center 2. What happens if a loopback is in my eBGP process in data center 1, and I interconnect the two data centers with each other, and it arrives on the other side? It will automatically propagate, right? So I need to go and filter it out. Why do I want to do that work? I'm not gaining anything. But I must filter it out, otherwise the tunnels go anywhere to anywhere. You guys following? I'm not advocating change whatever you believe in. I'm just advocating for simplicity. If I have two separate underlay domains and interconnected with eBGP, if I don't do redistribution, the routes are not propagated in between. That's my underlay domain. In the overlay, if I change from a AS to another AS, next hop, AS path, and so on, is happening automatically. It was done for that. And it was done for that not just now or 2017 when we started with this here. This was done like this all the way back when the first MPLS L3 VPNs with inter-AS options came in. You don't have to believe me. I'll just share it with you. If I have more than one data center, probably two, maybe I have n, take any number, the BGP connection between the border gateways can become a little bit cumbersome because full mesh. Some function which is called a route server, or in simplified language, an eBGP route reflector. Route reflectors are iBGP, so I cannot say that, so it's a route server. So I can connect my border gateways to that route server, redundantly, hopefully, make two up there. They're pure control plane reflection points. So I send it up there, sends the data down to the other one, meaning the BGP updates, the tunnel are formed directly. This is a way how you can simplify your BGP peerings between multiple data centers, or multiple sites in that case. This was a little bit of a detour, because I want to confuse you all and change your brains. You guys remember this? It's the network devices back. It woke up and it brought a little buddy. There's a little other network device there. Now we call it L. You remember that network device before we had? That was actually the little buddy L. So we defined L before in that very first packet walks, which is there, and host is connected to L. Everyone remembers? Yes? Yes? Do I have to recap it? Go to the beginning? No, I won't. But now I have there another network device which I bring in, and now I say between L and another network device I have a fabric. What is a fabric? It's kind of a leaf spine topology, whatever, some kind of IP routing connectivity. But that network device there, I put a VTAP on top of it. And now that network device becomes a network virtualization edge. But it's still a router, a bridge, a switch, or whatever you want to call it there. And let's expand the topology a little bit, because we spoke about host, leaf, and then there was a spine, and then we didn't know what the rest was. Then I spoke about multi-data center and multi-site and border gateways. So I will show you now how this all looks, what we initially had in there from a routing and bridging, if there is a border gateway in this world. And now you see the topology a little bit wider. We have our host body A connected to L, leaf. There is some kind of network in between connected to border gateway. We have some inter-data center link going to another border gateway. Then there's another fabric there. I don't know really what it is. And then there's probably a leaf and a host beyond there. So you see now how we got from a little focus to a multi-data center focus. We'll bring that along. And now we look, oh wait, before I go there. This border gateway is stitching between local VTAPs, meaning L, and remote VTAPs B. These are these split of topology which we spoke before. And then that other B does basically the same thing on the other side in inverse. Border gateway has tables. Border gateways has only two tables. Has a MAC table, has an IP table. Because of our first hop, our default gateway sits on L, which we defined earlier, right? I don't know. I don't need MAC IP binding. I don't care about MAC IP binding because I have no hosts connected to me. I already get EVPN updates, which is either the route type 2 or route type 5, which has all of these information in there. And that's what we're going to look at as we progress to these slides. So I'll make a case for something coming from Fabric 2. I have no clue what it is, but our route update will tell us. So what do we see? Something like routing, type 5, right? IP prefix route, 10.10.0/24. Single label, 50,000. A route target for the import into the VRF. A next hop, 10.021. 10.021 is who? Little b over there. And then X2, 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 X2 is little b's router MAC. Is this a valid MAC? Stops at F, right? I just made it for the purpose to show you a little bit different words and numbers and letters. Otherwise, it gets boring. So I get that update over EVPN, border gateway gets it, border gateway has a VRF definition, and the VRF definition, that's a route target import, and will import based on the information it has, the route target, this 10.10.0/24 with an next hop of 10.0.2.1 in the VRF8 table. When he receives that, because he is a gateway between the remote fabric 2 and the local fabric, it will take that information and will export it. That's the correct term. You can also say redistribute if you want to. Actually, it does export. That's the correct one. Or advertise it. So it takes this route and sends it to L, which is the leaf, over route reflector or not, I don't really care. And then L will import these information respectively. So let me show you how the routes look like. So now you see something has changed, which is next hop, router MAC. Next hop naturally changed because of BGP AS change. I come from remote AS to this AS. It's eBGP behavior. Router MAC, as an extended community, has been changed because we do a route reorigination with the right attributes. So the next hop fits what actually L needs in order to talk to border gateway to have an exit point there. Yes? Good? I'm not showing you what L has. We discussed L before. L is boring. This guy is much more interesting here, big BGW, big fatso. So remember, we also had some other routes which came in. Said host routes, MAC IP routes. MAC is mandatory, IP is optional. /32 or 128 is the only mask you have on the IP side. So somebody behind Fabric 2 there is advertising to be a route 192.168.112/32, 2 labels, 2 route targets, 2 next hops. So when border gateway Big O receives it, well, takes this information. Remember, we already had the 10.10.10 route before that came as type 5. So now we get the MAC address imported into VLAN 10. Why VLAN 10? Because there is a MAC VRF with a route target import, and that MAC VRF has a VLAN to VNI mapping, which fits label 1 and 30,001. So you configured it this way. That's why it's VLAN 10, or why I decided it's VLAN 10. At the same time, I do an import of the host route 192.168.112/32, next hop 10.0.2.1. Who is 10.0.2.1? Little b. Bzz. Okay, so we do the import. What happens next? We do an export. We send it into, yes, it comes. Here we go. We send it into the fabric itself. Here we go. And now what has changed is next hop and router MAC. So in fact, I lied to some of you. Actually, to all of you. There's one more thing that change. One more. Can you see it? So next hop and router MAC changed as we hit the border gateway and send it down to leaf. What else changed? Route targets, exactly. So in this diagram, or in these diagrams, I use a route target that is auto-derived. I can just say route target auto, and it takes the AS number of the device plus the VNI of the service. So as this comes from Fabric 2, which I assume is 65002, goes to big border gateway, and he does a reorigination of that route, we're now entering a different AS number, right? 65001. The default configuration is 65001, 30,001 or 50,000, right? If I do that auto derivation there. So we have a little knob which allows us to say that if BGW and little b peer to each other, and the neighbor AS is 65002, import it even as you are 65001. So you don't have to deal with manually configuring AS numbers and route targets for every VRF. You guys tracking on this one? Everyone? Yes? Tell me if not. We have time. You guys are so quiet. Is it too much? Yeah. Really? Really? Should I go back to the beginning? I can go through all of this in 20 minutes, I promise you. So some of these constructs which I try to explain, they kind of imply that you have a little bit of an understanding of VPN and BGP. I have a little bit of an understanding in VXLAN, specifically VXLAN EVPN. I understand. This is a lot of material which I try to cram. Actually, this is, I think it's 3 sessions of each 90 minutes condensed in one 90-minute session. So I understand. You guys, 90% of you, 99 will track anyway. You said you don't, so I'm sorry. You're the one. You said it, not me. So these VPN, these BGP VPN concepts are these days super important. How BGP works, how the VPN story works there. I made a lot of references to L3 VPNs and MPLS. It is really not a 2025 thing. We just reuse a lot of these old things, and we, over the last 20 years, okay, 30, I have to admit that I got very, very sloppy with terminology. We often talk about VRFs, right? VRF is on a box only. It doesn't exist on the wire. It's a local routing table thing. But often we say, I use a VRF in L3 VPN. Well, it's a VPN then, because it goes on the wire. And here, the VPN is the EVI. That's what I'm saying. I got sloppy with these terms. And as we started introducing this, I figured that we have to get more and more accurate on what is actually what and name it the right way. That's why I was so specific on the network device, the NVE, and then the VTAP, and what is the VTAP and what is the device. And I still got sloppy every other day or every other minute when I present something and just say, oh, this is the tap, and this is the switch or the router and so on, or this is a type 5, and this is this, and this is that. But ultimately, when we're doing these things, specifically me giving you a little bit of insights, I should be more and most accurate and try to give you the time to explain all of these things enough, which I unfortunately don't have. But I like all of you, that's why I did a little detour on this. So, I'll show you now how encapsulation works. We spoke about control plane. I know it's a lot. You guys get control plane, right? More or less. So like, it will work somehow. So this is now how the data plane works. So here, we have host A who wants to talk to somebody, and just based on my little gut feeling, I would say we have a communication between 192.168.0.12 and 192.168.1.12. One is a local host, host A, next hop 111, which is L, little l. And then we have 10.0.2.1, who is 10.0.2.1. 10.0.2.1 is actually little b over there. So this specific table view we have is from the border gateway itself. Yes? Okay. The red packet you see, or the red VXLAN encapsulation you see, is what you would see between L and BGW. You can see that based on the SIP, I'll try to point, it doesn't work, the SIP out there, 111, to 10.0.1.1. 10.0.1.1 is the virtual IP address of border gateway. So we're sending it up there. You see A1, 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 that's not the steak sauce, that's the MAC address, the router MAC address of L. You didn't get that, right? In the US, it works. It's the horrible thing. Here we are, eat steak without sauce, obviously. And then we have X1, 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 a MAC address that doesn't exist, but which is the router MAC address of border gateway. So we completed the inner headers. Source and destination IP is the same. This is red, so it means it's routed. That means the inner MACs are not the source and destination host MAC, it's the intermediate hop-by-hop MACs that come in. As we get that VXLAN encapsulated traffic to BGW, BGW will do some modification. First modification is the SIP and the DIP changes. SIP is now 10.0.1.1, that's himself. 10.0.2.1 is little b over there. So which means based on the tunnel instructions and the table information, that's where we send it. So the imposition is based on the destination IP address where that specific 192.168.112 IP address belongs to, which is somewhere else, right? IP address next hop, information, imposition of the same. X1, X1 is the source MAC, which is the border gateway's router MAC itself, his own personality on that level. And then X2, 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 we learned from little b as the router MAC in the control plane update. So when we want to send it there, we would need to use that MAC address. This is inter-subnet routing, pure routing. It's host 1 to host 2. Host 1 and host 2 is in a different subnet. That's why it's red. Questions? It's your chance.
Does the architecture change a bit if you had it disaggregated VXLAN?
Does the architecture change if you...
And the flow?
No. If you aggregate VXLAN. Oh, disaggregate? Oh, yes. Oh, that's a good question. So if you disaggregate the gateways,
correct. Yes. So if you
everything will change. It can happen. I mean, I saw people using these two-box kind of solution. The main problem you have, sorry for the detour a little bit, is that the tunnel from L to BGW exists. Then you break everything apart and make it IP Ethernet, and then you create a new tunnel from a new border gateway or new gateway to the remote side. So you would have Ethernet information in the middle there. And do you know what VRF light is? What is VRF light? Per VRF peering on a link. So think if you have more than 2 VRFs between the 2 nodes and you have to do all these peerings and stuff, it becomes very cumbersome. Okay, let's look at the bridging case. Again, some form of shape. I know that 192.168.1.5 exists and 192.168.1.12. I have it here. Same subnet, so we guess it's bridging. I would just 50-50 chance that that's what it is. You see now that when we come from host A, we go to little l. Little l is 1111. Destination IP is border gateway, which is 10.0.1.1. We see now we have a bridging VNI, so there's a layer 2 VNI, which is mapped to the MAC VRF. And then you see that the source MAC address and destination MAC address of the host is transparently visible. You see the 100A and 100B? We're not changing to the router MAC address because we do bridging now. So it stays in there as the inner MAC addresses, source MAC and destination MAC, and you see the source IP destination 1.5 and 1.12 being there. So now given the next hop is 10.0.1.1, we send it to the border gateway big there, looks at it and said, hey, this goes to 112 or 100B. They sit behind 10.0.2.1, that's the remote border gateway, so let me do the encapsulation for that. SIP is 10.0.1.1, DIP is 10.0.2.1. So that is the outer tunnel information. We know we do bridging. Why do we know that? Because it's the same subnet in there. We haven't made a default gateway change decision on leave before. So the source MAC destination MAC stays the same as it came from the origin of host A as it goes to the destination, which could be host B or the like. So we're not changing anything hop by hop as we do in routing. You get the differences between the routing and the bridging, how the MAC addresses and the IP addresses change. Yes? You guys have to tell me if not. I can do a detour and get you through that part.
No.
No? You do?
I do not.
You do not. Okay. In the case of host A wants to send something to another host remote. Let's go here. If host A, source IP address 192.168.0.12, wants to communicate to 192.168.1/12, host A knows that this is not same subnet because of the mask that is configured, so it sends it to the default gateway. 1.1, for example, or in that case, 0.1 to be correct. How does it do it? It sends the traffic still to address 1.12, but the destination MAC address from host to default gateway is the destination MAC address of the default gateway. That means that L, who hosts the default gateway, is not doing a bridge forwarding decision because it's addressed to himself, but he does a routing lookup. Now, as he did that routing lookup, he doesn't care what the remote MAC address is of somebody because it's a routing instruction. We don't need to know about the MAC address. And he also doesn't care what the source MAC address was for everything going forward. So that's why you see there the change of source MAC A1, 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 which was the original, apologies. A1, 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 you don't see the MAC address of the host A anymore, but the one from the leaf, which was the default gateway for the routing process. Does that help? I appreciate that you said that because I'm sure everyone else in here liked that explanation too. Is that correct?
Yeah.
Here we go. You guys are okay. We have time. We're good. Okay, so we're at the end. I have hoped that there were maybe more questions, so I'll stay just at the end. But I give you, don't run for the door, I locked it. I give you a little bit of a conclusion here. So there are two main things which I touched in this presentation beyond the packet walks, which is what is multi-site, or more specifically, what is that border gateway, that tunnel stitcher. It will show up and be a solution for you in so many use cases. That's why I wanted to have that in that middle section when it goes into design and the reason on why we're doing this. You remember we had these two different modes, the Anycast and the VPC border gateway. We had all of these different use cases. It is a tool in your toolbox. It doesn't say you need to introduce it in every single opportunity you have to introduce it. But if you get into complicated cases, it might actually help you to fix things. The border gateway is not a hammer and everything you see is a nail. Good?
So that was my question earlier, right? So you have, you got your border gateway, right? That sits on the edge of your DC.
Yes.
And within the DC, you've got a
Leaf-to-leaf to communication directly.
Yeah. However, in this case, you have the control plane centralized. You have a route server, which is IBGP.
Yes.
Talking to your leaf.
Yes.
That one DC.
Yes.
So would that scenario work with the border gateway scenario?
Yes.
Yes or no? Okay.
Yes. So you have leaf spine, route reflector, IBGP or EBGP, whatever else within a data center. You can add it for inter-data center or you cannot do it.
It's a centralized control plane.
Yes, you can.
Yeah.
You have that option there. It's an option. That's what I'm saying. It's an option. It's a tool in the toolbox. The second piece which we spoke about is just overall VXLAN EVPN, right? You remember when I started explaining route type 2s, route type 5s, and so on and so forth. And then we introduced a little bit of that multi-site concept that we expand into a little bit deeper on that whole RFC combination and what you can do in these different functionality. I don't know, but these days I literally have close to zero conversation of VXLAN EVPN without a border gateway conversation. Either I'm very biased, or we solved kind of a piece in the market at that point when we started doing this. So I'll say thank you for being a good audience. Appreciate it that you were here. Didn't fall asleep. I had some snoring in the back there. Enjoy the rest of your time, and I'll see you all next year, I guess. Thank you.